All right, I want to talk a little bit about the B-spline recursion formula. So any B-spline can be written as follows: B di of t. It's going to be written as a sum where I have some fraction in front and a lower degree B-spline. And so this is going to be BD minus 1 I of t. So we have the lower degree B-spline with the same index, I, and then we have another lower degree B-spline with the index 1 forward, or 1 more than I. So what goes in as the coefficients? Well, let me also just make a notation here. This B-spline uses the knot values ti through ti plus d plus 1 in its definition. If you remember the divided difference definition of the B-spline, this was in the bracket operator, right, that uses those knot values. Similarly, if I have a B-spline of degree lower, it starts with I, but it goes up to I plus d minus 1 plus 1, which of course is just t plus I plus d. So this would be using the knot values ti through ti plus d. Then finally, this B-spline of degree d minus 1, this would be using the knot values ti plus 1, and then through I plus 1 plus d minus 1 plus 1. So that adds up to ti plus d plus 1. Okay, so these are the knot values that are used in the definition of each of these B-splines. What goes in the denominator for each of these is just the last knot value minus the first knot value. Okay, so the last knot value here minus the first knot value. And then what goes in the numerator here is just t minus ti. And that's going to be a value which evaluates to 1, of course, at ti plus d as a coefficient for this B-spline. All right? And then this one is going to be ti plus d plus 1 minus t. So notice that in both the numerators here, I have a linear function. And this, of course, is just a constant. So in fact, I've got a linear function times a lower degree B-spline and another linear function times a lower degree B-spline. Okay? So let's just do, and I should say before that is, I should say that this formula, right, applies for, certainly in this case, for degree greater or equal to 1, right? Remember that we only have polynomials down to degree 0. So if I'm going to build a degree 1 polynomial out of, or B-spline made out of polynomials, right, of degree 1, I can use degree 0 polynomials here and then linear factors in front that will bring it up to degree 1. So we only start with d greater than or equal to 1, right? What are the I values? Well, the I values, remember, they always come from some knot sequence t, right? And so t is given as t0, t1, and so up to tn. And so all of the B-splines in this formula are defined with this knot sequence, right? So whenever we define some B-splines and we have a formula regarding those B-splines, we have to have a degree and a knot sequence in order to make sense out of those. In some cases, of course, the B-splines will be a basis for our vector space, but now in general they don't have to be always they don't have to be actually a basis. Okay. So for example, let's just look at, it helps to have a picture in mind. My favorite picture in mind is to do the degree d equals 2 case, where we get a degree 2 B-spline made out of some linear B-splines. Okay, and so how does this look if we graph it for t0, t1, t2, and t3? Those are the knot values that I need in order to make b20 of t. And remember that the b20 function looks like this. It's quadratic polynomials coming down like that. We're going to build that out of 2 linear B-splines. And so those I'll draw dotted like this. these are what we also just call hat functions. Another name for linear B-splines is hat function, because of the hat shape. If we take these two hat functions, first of all, let's just write out what these are, right? This would be B10 of t. So that's including this part. And in fact, of course, any B-spline is actually defined for all t. Okay, it's just this bump is the only non-zero part. And then similarly, this bump here is the linear B-spline B11 of t. Remember, the lower index always tells us where the non-zero part of the B-spline starts at index 1 here. This one starts at index 0. They go for 3 knots because that's linear, 1 plus plus 2, right? So in other words, I'm always going the number of knot values that I actually use, right? Ti from Ti to Ti plus D plus 1 is in fact D plus 2 knot values. So what does the quadratic B-spline look like then? Well, as we said, it goes up like this, and then over like that, and then down like this. Okay. So the idea here is that we take linear factors and multiply these to get, and then add them together to get the sum being this quadratic B-spline. This is B20 of t. And according to the above formula, right, B20 of t is indeed, I take B10 of t, and then I add that times something times B11 of t, so it's definitely those two linear B-splines put together. Here I get t minus t0, right? And then I get t0 plus 2, right? Degree is 2, so I get t2 minus t0, right? And remember again, that I was pointing out before, that the t2 minus t0, that's the last versus the first knot, last minus the first knot for this linear B-spline, which is this guy here, okay? And in the denominator on the other one, we'll throw that in here, that's going to be t3 minus t1. And then this is just t3 minus t. Now, one reason where you can see that in fact, you might be wondering, why do we swap the t minus a constant and then a constant minus t on this side? Well, the parabola here, which is defined by t minus t0 times something going up here, right? You can see that in fact, we're going to have this linear B-spline is a linear function which actually looks like the line t minus t0 here, right? If I multiply that by another t minus t0, I'm going to get t minus t0 quantity squared. And in fact, that's exactly what the parabola t minus t0 squared would look like here, right? Then of course there's just some other factor. So then we can always scale things. And that scaling comes in importantly later when we see that the sum of the B-splines is again going to be actually equal to 1. All right, so we've got that one. Then what about on this side? Well, here we've got the line going down, right, which is actually not t minus t3, but the negative of that, because I've got a negative slope. So this is t3 minus t. So it's a factor of this type, all right? And then in the linear B-spline function, it matches, the t3 minus t matches this factor. And so we get a t3 minus t squared. Now in the case of quadratic, of course, it doesn't matter in the end if you have this t3 minus t squared or t minus t3 squared. But when we get up to different degree B-splines, that does matter as well. And so we'd be taking the piece of the quadratic here that matches the final graph for the B-spline. That's not a proof that this formula works and gives us this shape, but it's just a kind of looking at the different parts of the B-spline and how they fit into the recursion formula, because it is a very important formula. Now, a couple of other comments about the recursion formula. Okay, one of them is that in many texts, this recursion formula is used as the definition. So this is used to define B-splines. But one of the things about that
is if you use this as the starting point, then of course you need to have a base case, and you also need to say what happens in cases where in the knot sequence I get equal knot values, and that sometimes these can collapse down and give us a 0 in the denominator, all right? So this is used to define B-splines with a few caveats. Okay, so the first caveat is the base case has to be explicitly defined, right? And that's of course for degree 0. And so B0I of t is just defined to be the function which is given as the constant value 1 on the interval ti to ti plus 1. Now remember that our spline functions are right continuous, at least the ones that we're using to define vector spaces of spline functions. Those are going to be right continuous. Inside the definition of the B-spline with the divided difference formula, we had a left continuous B-spline as a function of, a left continuous truncated power function spline, right, as a function of x. That's the only case where we really need to use left-sided or left continuous spline functions. In general, when we define them for vector space bases and so on, they will be right continuous, and so that would be the picture, right? As I approach ti from the right, I am actually approaching the function value, right, at the point ti. As I approach here, again, the value is here, not up here. As I approach from the right, I'm approaching the function value. If I approach from the left, I have the value 0. I'm not approaching the function value, it has value 1. So there's a difference, there's a disagreement between the limiting value as I'm approaching ti, which of course is 0 because it's constantly always equal to 0, and the actual value. They don't disagree. They don't agree, those disagree. So same thing happens here. If I approach from the left, I'm now having a constant value of 1, but the actual value of the function is down here at 0. Okay. So indeed, this is a right but not left continuous function. How is it defined then? As the base case, we just set it equal to 1 for t in that interval, so ti less than or equal to t less than ti plus 1, and then 0 elsewhere. Okay. So this gives us the base case, and then the other caveat, if you're going to use the recursion as the definition of a B-spline, the other caveat is that you have to say what happens when you get multiplicities, right? So that tells me if ti plus d equals ti, that will only happen, of course, because a knot sequence, remember, is non-decreasing. So ti plus 1, etc., all the way up to ti must all be the same, right? Then in that case, then we declare this B-spline, if there's a 0 in the denominator, we just declare that B-spline to be 0. So bd minus 1I of t to be defined to be identically 0, okay? And we skip this term. So we skip the above term, t minus ti over t I plus d minus ti bd minus 1 of t. In other words, we just declare this function to be 0, and we skip this term in the recursion formula. It does indeed all work out then. Well, rather than defining them this way, of course, we are defining the B-spline using the divided difference formula. And when you use the divided difference formula, let me just write it down here one more time. This is actually the actual definition of B-spline that we're using, bdi of t. Remember, it's just this constant minus 1 to the d plus 1. Then I get ti plus d plus 1 minus ti. And then I get those knot values that go into the bracket operator. And then I get t minus x to the d plus. When we use this definition, we will see that the degree 0 case just comes out naturally from this definition. There's nothing extra that we need to define. This function right here comes straight out of the definition. And then when we talk about the recursion, all right, this B-spline will in fact be 0. And you can see that in the case that ti plus d equals ti, right, it would mean that this factor right here already kills off the whole B-spline, and it's actually defined to be 0 there, okay? So then the only other thing is that when we talk about the recursion, all right, we only talk about adding up sums of B-splines when a B-spline is non-zero. So we don't actually then attempt to compute this quotient, or this rational function here with the denominator that would turn out to be 0. In that case, we already know that this B-spline is 0, and we don't compute this value, and then all the recursion works out perfectly.